So quantum dynamics. Now, you know that if the psi 1 of x and t, comma psi 2 of x and t, these are solutions of the Schrodinger equation. That means if these are solutions of the Schrodinger equation, then a linear combination of them is also a solution. So we can say that x and t, this is capital psi, meaning the time dependent, these are not the eigenfunctions in that sense. So a1 of psi 1, actually these were only functions of x, sorry, let me just cut it off. These are only functions of x, plus a2 psi 2 x, and so an. So basically what we have said is that if each of these are solutions of the Schrodinger equation, so is a linear combination. So that is also a solution of the Schrodinger equation. Now in your tutorial problem that I gave, you are given a particular initial state psi x 0. Now that initial state can be thought of also a linear combination of all this. So the way to solve that problem was initially to think the initial value as like this. So x psi x 0 is a1 psi 1 x plus a2 psi 2 x, and so on. And then to obtain the values of a1, a2 and all that by the process of computing the overlap integral. So you will calculate the overlap integral between the initial wave function and each of these eigenfunctions, and that way you will compute the a1, which means that how much is the initial wave function similar to the first eigenfunction, how much is the initial wave function similar to the second eigenfunction, and so on and so forth. These give the a1, a2 in such a way that a1 square plus a2 square plus a3 square, all that root is 1. So now after that, all you need to do is to plug in these positions the phase factor, and that gives the Schrodinger equation's solution. That is what you had to do in the last class. For today, to start with, let us consider only two of them. You assume that only two are there, maybe the ground state and the first excited state. And so your psi of x and t is equal to a1 psi 1 x. I will put comma t because now I will put the phase factor also, plus a2 psi 2 x and t. Only two of them are there. And if you actually put the phase factor, it becomes psi 1 x e to the power minus I e1 t by h cross plus a2 psi 2 x e to the power minus I, now e2 this time t by h cross. So this is how it evolves. So when you talk about the evolution, these phase factors are there. Now, you might have been told that the phase factor actually do not have any effect. Yes, that is true, because if only this part is there And if you are trying to construct the mod psi square, then this term actually disappears. But when you are trying to talk about the whole evolution, these terms do not disappear. Just let me show you that these terms do not disappear. If I want to calculate the psi star psi of this one, so we are trying to calculate the psi star psi. Let me start from the left so that we have more space. Psi star psi. If you want to calculate that, then this term we'll have to write first the starred term. So it will be A1 star psi 1 star. Let me not write function of x because that will only clutter the notation. E to the power, now this will be plus, be star, plus I E1 t by, okay, plus A2 star psi 2 of x. I will not write the of x to make things simpler. Psi 2 e to the power plus I E2 t by h cross. If my picture is there, then the file size becomes larger. So those of you with some weak internet connection may find it difficult to download it later. So let me switch off my video and then let me continue. Probably that will be easier for you to see later. Okay, then I have to write this part, psi t. This will be A1 psi 1 e to the power the same thing, minus I E1 t by h cross. I'm writing faster so that you don't spend time. Psi 2 e to the power minus I E2 t by h cross. If you multiply them, first this one gets multiplied with this one. You can easily see this and that cancel each other, and this and that effectively gives A1 mod square, then psi 1 mod square, only this much. And when this one is multiplied with that, you get A2 mod square, psi 2 mod square. Then the cross terms actually remain. And the cross terms will give, I can see that A star, A1 star, let me pull down this so that we have more space. A1 star, A2 psi 1 star psi 2 e to the power E1 here, E1 here, E2. Okay, so this will be e to the power I E1 minus E2 t by h cross. That's the first term, and the second term will be plus A2 star A1 psi 2 star psi 1 e to the power psi 1 e to the power I E2 minus E1 t by h cross. See, these two terms survive, and therefore time dependence survives. So even though you might have been told that these phase factors do not have effect, they do. When you consider the whole time dependence of the wave function that comprises more than one eigenfunction. Is that clear? Let me illustrate that a little more elaborately with, let me erase this because have you noted this down? because I need space. I won't have that much space in the bottom.
Yes.
Yeah, so let me erase this and let me illustrate it a little more in details. Okay, let me put it up. Yeah. Now suppose we consider a harmonic oscillator. The harmonic oscillator is something like this. We had a classical harmonic oscillator whose quantum analog we are talking about. So this is a C and this fellow is a M. And then your, let me write in this side all this stuff. The potential function was half Cx square, or this was also equal to half m omega naught square x square. Okay. We also learned that omega naught in this case is root over c by m, and the time period was 2 pi by omega naught. These are simple stuff you probably learned in the first year, so I don't have to repeat in details. And for the quantum harmonic oscillator, you have learned that the ground state wave eigenfunction is it will be 1 by root pi a to the power half e to the power, say, Gaussian function x square by twice a square. And your, let me write here itself, psi 1 first excited state eigenfunction was, just recapitulation because this is something you have done already, 2 square root pi a square root and twice x by a e to the power, again the same thing, minus x square by twice a square. If you recall, your a was is a typical length parameter, was h cross by m omega naught. Okay, so this is the background in which we are working, and we are talking about a particular initial or a particular wave function that comprises these two. So if I now put it, your psi x comma t, because I will now put in the phase factor also. Let us make them equally. That means half of it is this, half of it is that, and if you put it that in the wave function, it will be 1 by root 2 because the square of that has to be there. 1 by root 2 of this, 1 by root 2 of that. It will be psi naught x, and then the phase factor will be minus I. Now, the energy of the ground state, which you know to be half h cross omega naught, this is the energy, t divided by h cross, and these two cancel off, plus again 1 by root 2, this thing, psi 1 of x. Again, in this case, it will be e to the power minus I. Now it will be its own energy, which is 3/2 h cross omega naught t by h cross. These two cancel off. So what you end up with are these. Now let us consider what is the actual thing when t is equal to 0. So at t is equal to 0, what will remain? Then psi x 0 will be this will go to 0. This will go to 0. Therefore 1. So it is 1 by root 2 psi naught x, and this will go to 0. So plus 1 by root 2 psi 1 x, right? And at t is equal to half the time period later, where your time period is here, half the time period later. So this t by 2 is omega naught. Half the time period later, it will be, sorry, it will not be small psi, it will be capital psi. Psi x. And this will be t by 2. What will it be? Now, if you put t by 2 there, so it will substitute it there. If you substitute there, then it becomes 1 by common psi naught x e to the power now minus I, and this will be omega naught by 2 pi by omega naught. So omega naught cancels off. What remains is pi by 2 plus psi 1 x e to the power minus I, 3/2 was there, and then this will be omega naught pi by omega naught, cancels off. Okay, so this is what we end up with. You can see that there's a great simplification, 1 by root 2, and now this is essentially if you now break this into cosine and sine, then it will be sine naught. Can you just do it yourself? It's a good exercise to do that yourself. If you break that into cosine and sine, it will be cos pi by 2 minus I sine pi by 2. Sorry, I will not use this. This will not be there. You have to add up. Plus psi 1 x times cos 3 pi by 2 minus I sine 3 pi by 2. Okay, and this is simply 1 by root 2. These ones cancel off, only remains this part, sine part. So you have I comes out here. What remains is minus psi naught x plus psi 1. This is what remains. So you see, at time t is equal to 0, this was the expression. At time is equal to t by 2, this was the expression. In one time, it adds up, another time it subtracts. Let's see how it looks physically. Your ground state wave function is like this. The first excited state wave function is like that. And if you add them up, you get something like this. And if you now take this one positive and that one negative, well, here these are the psi naught, this is psi 1, but here I'm plotting psi mod square because I don't want any negative number. And if you want this, it is this minus this. So in the negative side, this will be taller. In the positive side, it will be smaller. So if you make mod psi square, it will be. So you see, at t is equal to 0, it is like this. So the hum is in the right hand side, and at t is equal to t by 2, the hump is in the left hand side. Again, if the hump goes to the right hand side, so it's lossless. I've understood how it actually is behaving. And is that clear? Is there any question? Just ask. Is there any question? No. Okay, good. So let us now take a even more closer look, because I can see the expectation value here and the expectation value here would be different. So now I will not ask. Now ask, what is the expectation values dynamics? How does it change with time? If you want to calculate that, let me again delete this part because we need board space. Something remained. We know that the expectation value of, expectation value of x is given by the sandwich integral minus infinity to infinity psi star xt. Then you have to sandwich it with this, and then psi xt. This is the expression for the expectation value. So if you now want to put whatever we calculated there, I have just erased, so let me write again. What we have written is that our psi star xt will be 1 by root 2 psi naught star e to the power, now it will be plus because psi star we are doing, plus I omega naught t by 2 plus psi 1 star e to the power 3 omega naught t by 2. This was the psi star part, and the psi part was, I'm just rewriting so that we can use this in the calculation of this. It will be psi star psi naught e to the power minus I omega naught t by 2 plus psi 1 e to the power minus 3 omega naught t by 2. Okay, now we have to plug it here. Now you can easily see that when you plug in here, there would be 4 terms. There are 2 terms here, there are 2 terms here, multiplication, and therefore 4 terms there. So let me write the 4 terms. It might initially look a bit formidable, but you will soon see that that formidable thing disappears. 2 of them, so it will become half minus infinity to infinity. First, we'll consider the psi naught with psi naught. It will be psi naught star x psi naught, the first term, dx, plus half minus infinity to infinity psi 1 x psi 1 dx, 2 terms done. Then, well, in these 2 terms actually cancel, these 2 terms cancel off, but then when you cross multiply, these terms will remain. So then it will be plus half. Now if you cross multiply, it is 1 and this is minus 3, so it will become e to the power minus I omega naught t, and then that will come out minus infinity to infinity. It will be psi naught star x psi 1, and it is the same thing, plus of e to the power, this time it will be plus I omega naught t integrated to infinity psi 1 x psi 1. You see, there are 4 terms. Now, have you learned in the last semester how to handle this kind of integrals? Because psi naught has an expression. Psi 1 has an expression, which I wrote in the a few minutes back. X as an operator is multiplication by x. So you might actually substitute the expression for this, x here, expression for this, and integrate. That will be a horrible integration. So this horrible integration can easily be simplified if you use a trick. The trick you learned in the last semester, that is, we learned things in terms of the raising and the lowering operator, right? If you want to express things in terms of raising and lowering operator, you know that x, this is something that we learned in the last semester, a by root 2, the a plus a dagger. Okay, this is what you learned, no? Can somebody unmute and talk? Can somebody unmute and talk?
So I think we didn't use the raising and lowering operators for the simple harmonic oscillator.
Oh, then how did you obtain the solution of the?
So we learned about the raising and lowering operators, but this expression that you have written, right? X hat is equal to a by root 2
Yes, yes.
So that we had not seen earlier.
But you know.
Yeah,
but
we know what the raising and lowering operator.
You know that a raising operator is 1 by root 2 x by a minus a. This is what you know, right? And the lowering operator is 1 by root 2 x by a plus. Right? This is what you learned earlier. The definition of the two operators.
Sir, we would have an I also, right? X by a minus I del x.
No, it should be x minus ip and plus ip, and p has an I factor in it, so there should not be an I.
No, the question is that these expressions of the a and a dagger, if you know, then it's simple to extract the value of x, right? It's not.
Yeah, got it.
Yeah. So if you do extract, then the advantage is that we can put this here, this here. The main advantage is that then a and a dagger will become separate operators operating on this. Now a operating on x naught gives 0. Therefore, the whole thing becomes immediately 0. You see the advantage. A dagger operating on x naught gives x1. Sorry, this should be psi. Why have I written x naught? This is psi. Yeah. So a operating on psi naught gives 0. A dagger operating on psi naught gives a psi 1. And you know that psi naught and psi 1, their overlap integral is 0. Therefore, the whole thing is 0. You see the advantage of this substitution. So this term becomes 0. So let me how do I write to make it simple? I write it this way. This whole thing will become psi naught star a plus a dagger operating on psi naught, this will become 0. This one, here same thing happens. A and a dagger both are operating on the psi 1. Now when A operating on psi 1, it gives psi naught, and the overlap integral of psi 1 and psi naught, because they are orthogonal functions, is 0. Therefore, the first term is 0. The second term, a dagger operating on psi 1 gives psi 2. And then psi 1 and psi 2, they are also orthogonal to each other. Therefore, this integral is 0. So this integral is also 0. Right? Let's talk about this integral. This integral is, let me write it once, minus infinity to infinity. It will be psi naught star a dagger, a plus a dagger, psi 1 dx. This will be minus infinity to infinity, and then it will be psi naught star. Now this operating on this, it will become, firstly it will, this is what? This one was psi 1, sorry, psi 1. So A operating on psi 1 will give psi naught. So it will be a psi naught first term. Second term will become plus, it will become psi 2, and there will be a root 2 of up front. But when you operate on this and when you operate on that, you can see that when you operate on this, not operate, if you just make the product and integrate, this will become just 1 because psi naught is normalized. When you multiply this and integrate, it will become 0 because these two are orthogonal to each other. So simple. So this one is 1. Similarly, you can see that this will also become 1. So now you can see that what has happened is this whole thing, your x, this is what we set out to calculate, has become a by root 2. It will become half e to the power minus I omega naught t times 1 plus half, this is all that has remained, I omega naught t. And this is something that we know. This is simply a by root 2. This is cos. So out of all this, the simple conclusion is that the x, the expectation value x, will oscillate cosinusoidally with a frequency omega naught. And it is the same frequency at which the classical harmonic oscillator oscillates. So here, the expectation value will oscillate exactly in the same way. And if you do the same calculation for px, then you will find that also oscillates in the same way, and you will ultimately end up with the conclusion that this oscillates like this. Sine. And in the classical harmonic oscillator, the x and p, the position and the momentum, oscillate, one cosinusoidally, another sinusoidally, here also doing the same thing. Only difference is that here we are talking in terms of the expectation value of a distributed function. Expectation value that to obtain out of a distribution function. We don't know where the particle is. We do not know really what the momentum is. These are undefined quantities. There is a probability distribution. But still, the expectation values behave exactly in the same way. Okay, have you understood the issue of the dynamics? If there is any question, you ask. Else we'll continue. Is there any question? No. I suppose you have learned also about the dynamics of the free particle. For a free particle, let me bring it down. Particle. Where the potential function is 0, you know probably that you have learned probably the last. If you have not learned, then you will just tell me. It will be 1 by this expression you learned last semester. Can somebody unmute yourself and talk?
Yes, sir.
You have learned this, right?
Yes.
Good. So this essentially embodies the dynamics of a free particle. And you know that the way to normalize the wave packet of a free particle is just to ensure that your minus infinity to infinity, your ak, this function square. If you ensure that, then it also ensures the psi star psi or mod psi square also is integrates to 1 by Plancher's theorem. So effectively here, you will find that you may have a function something like this to start with. That means the particle has a larger probability of being here, a smaller probability of being there, smaller probability of being there. But as time progresses, if the initial wave function psi is real valued, have you learned that in that case the expectation value of the momentum is 0? That result did you learn in the last semester? Can you just unmute and talk? I'm saying that, say, initial wave function, the initial wave function.
We didn't learn it explicitly, but he mentioned that in class once.
Okay.
Because you won't have an eigenfunction corresponding to it.
Yes. Here, if the initial wave function is real valued, then its momentum distribution is such that the expectation of the momentum is 0. So if the expectation value of the momentum is 0, the particle actually does not move. But since there is a spread in the values of momentum, that means momentum is not exactly known. Therefore, what will happen is that as time progresses, this will spread. So it will become something like this as time progresses. So even though a real valued initial wave function of a free particle may not move in space, but it will spread. But if it is a complex valued, then there will be a finite valued momentum expectation value, and it will move. Okay. So far, I was sort of recapitulating what you are supposed to have known in the last semester. That is necessary because, well, there has to be smooth movement into the next course. But for the next class, I'll start things that are new. And so you should attend all the classes and take class notes, because you can see that after I finish a particular board, I erase it off, so that doesn't continue. So you need to take class notes. That is for your own economy of time. If you do not take class notes and think that I will listen to it later, you will end up spending more time.